Solving problems like this one requires you to use the conservation law of energy to analyze each of the scenarios found within. You have an object that starts at the top, has a certain amount of potential and kinetic energy. Those two energies added together make up the total mechanical energy of the object. And the conservation law for energy tells us that as long as there are no external forces like friction and air resistance, which we are ignoring in this problem, the total mechanical energy has to stay the same throughout the entire run. The individual potential and kinetic energies are going to change, go up and go down, but together they will always add up to the same total. So it's really helpful in problems like this to be able to start by calculating the total mechanical energy of the object, and we can do that because we have enough information to solve the potential and kinetic energies of the object at position 1. So let's start with that. We're given an object's mass. It's 50 kilograms, and it's perched 4 meters above the surface. So we can solve for potential energy using our equation m times g times h, and that will look something like this. Potential energy at the start is the mass of 50 kilograms times the acceleration due to gravity, 9.81 meters per second squared, times the height of 4 meters. And when you calculate that, you get an answer, 1,960 joules. So that can go here, our potential energy at position 1. We also can tell just by looking at the scenario that this object is at rest. It's perched here on top of the ledge. So the total velocity is currently 0, and it doesn't take a calculation to get the kinetic energy must be 0 as well. Kinetic energy is 1/2 of mv squared. If v is 0, the kinetic energy is 0. And since the mechanical energy here is just the sum of potential and kinetic energies, 1960 plus 0 gives us a mechanical energy that is also 1,960 joules. The next step is again to realize the conservation law of energy tells us that the total mechanical energy here is constant across the board. So I'm going to start by just filling in all of my mechanical energies as 1,960 joules. That is the number that cannot increase or decrease without an outside force involved. Now we can take a look specifically at scenario 2. Scenario 2, the roller coaster is located here at the top of the loop, and we're told the height at the top of that loop is 3 meters. Height is a clue about potential energy, so we'll calculate the potential energy on the top of that loop as mass, 50, times g, 9.81, times a height of 3 meters. And that potential energy works out to 1,470 joules potential. And because the potential energy here added to the kinetic energy here has to equal the mechanical energy, we can solve for kinetic energy through simple subtraction. 1960 minus 1470 gives us the kinetic energy, which works out to 490 joules. And the last piece of this is to solve for velocity, which we can do now that we know the kinetic energy, because the kinetic energy, 490 joules, is equal to 1/2 the mass times v squared. And when we solve for v, we get a velocity here of 4.4 meters per second. And that finishes location 2. Location 3, right outside the loop, we can see the object is at ground level. So the height here is 0, which makes for a very simple potential energy calculation. If your height is 0, you have no potential energy, no gravitational potential energy at least. And so we can figure out kinetic energy again by looking at the total of PE plus KE equals ME. So this kinetic energy has to be 1960. It's the only way to make them add up to the total mechanical energy. And so we can solve this in much the same way we solved number 2. We're essentially just taking out the kinetic energy of 490, and we're replacing it with the new kinetic energy at position 3 of 1960. So the same algebra solution with just a different starting point. And we get a velocity here that's equal to 8.9 meters per second. The last location, location 4, gives us some different information. We're told the velocity and asked to figure out the height. Well, the velocity is information that, along with the mass, allows us to calculate kinetic energy. So over here we're going to solve kinetic energy using 1/2 of m times v squared, where we actually know the v in this case. So 1/2 of 50 times 6 squared gives us a kinetic energy here of 900 joules. And now we'll use that to go back to the potential energy, since that potential energy, again, plus kinetic equals mechanical. If there's 1960 joules of total energy and 900 of those are kinetic, that means what's left for potential is 1060 joules. And once you know the potential energy is 1060, you can plug it into your MGH equation. 1060 equals 50 times 9.81 times the height we're solving for. So divide by 50, divide by 9.81, and you get a height of 2.2 meters. So there's a lot going on in this problem for sure, but if you take it on one step at a time, each individual calculation is not too bad. It's either a calculation of potential or kinetic energy or subtraction using the mechanical energy conservation concept.